Imagine a single data center campus with the energy consumption equivalent of a small city to provide the AI-accelerated capacity to power the most advanced AI training and inferencing workloads. Today, we will explore state-of-the-art engineering that enables OCI to build and operate AI data center campus at unprecedented speed and massive scale. Welcome to First Principles. We are on our way to launch many gigawatt-sized data center campuses to host some of the largest AI superclusters. These superclusters will be used by our customers to serve the most demanding AI research and production workloads. For comparison, the city of San Jose uses around 1 gigawatt. Essentially, we are talking about a data center campus that consumes the same amount as a city. Now, these gigawatt-scale data center campuses that are used to build our superclusters host very large AI training jobs that can essentially make the entire data center campus go through load oscillations based on the phases of the training job. As an example, when the training job goes through a checkpointing, it creates a lull in the compute load because the entire network is busy sending packets back and forth. And then once that's done, the load goes back up. These load oscillations can be challenging for the power infrastructure to handle, given the scale, and it requires special engineering at the data center level. The power consumption of a city, if you think about it, is not constant and varies on a continuous basis. But the scale of load oscillations can be much higher with data center campuses. Additionally, the gigawatt-scale data centers typically host high-density GPUs and other AI-accelerated chips that require special engineering to cool them as well. Joining me today to unpack the power management for hyperdense GPU data centers is Ram Nagappan, Lead AI Infrastructure Architect. Welcome, Ram.
Thanks, Pradeep. Happy to be here.
So, OCI has announced plans to bring multiple gigawatts of data center capacity online in the next few years. What are the core differences between traditional data centers and large, superclusters built for AI from a power management perspective?
There are two key differences. One is the size, and the next one is characteristics. If you look at the data centers maybe 3-4 years ago, they may be anywhere 5, 10, 20, 50 megawatts. Now, if you look at the AI data centers, they are anywhere in the 100 megawatts to some of them can even go beyond 1 gigawatt. The size is different. The next one is the characteristics. What I mean by that is the workload that's running on the data center. If you look at the earlier data centers, you may have compute, storage, different kind of workloads running. So the power doesn't fluctuate a lot. But if you look at the AI workload data centers, there may be a few 100,000 GPUs in one data center. And when the workload starts to run, it can go from like a 30% to 100% instantaneously. And they may run for like a few minutes. Then due to checkpointing or due to synchronization, the power can come down. So that's a new characteristics that's not common with the earlier data center. So those are the two key big differences.
What kind of problems can they actually cause when there's load oscillations?
Yeah, typically during load oscillations, voltage and frequency change momentarily because, for example, if you take the scenario when the workload goes from 30% to 100%, so there is going to be a voltage dip because that's how generating equipments now need to generate more energy to bring the frequency back and the voltage back to the nominal level. So in the previous cases, like if you go back 3-4 years, it doesn't happen like suddenly going from 30 to 100%, or when the load comes down, let's say 100% to 30%, that is a huge frequency dip also. That doesn't happen. Now, the data center needs to care about it, the equipment, and also the utility needs to care about it, how to handle those wild power swings that is really unique to the AI workloads.
Got it. So essentially what I'm hearing is, when the load oscillation is natural for, the voltage and the frequency to vary. And in fact, it is actually the signal to make adjustments to the generation equipment itself to speed up or slow down or maybe turn off or do some control. And that works fine as long as the changes happen at a smoother phase, if you will, but not necessarily when it happens too steep for it to handle. Is that what I'm hearing?
Exactly. So instantaneously, utility cannot handle this. Their generating equipments cannot go suddenly from 30% to 100%. Each one has a different ramp rate requirements. Some have like a 1% ramp rate, or some has 0.5%.
1% for a second?
Yes,
or minute?
yes, 1% per second. That means you got to gradually, step by step, you got to go up.
On 100 seconds, you can actually go from 0 to 100%.
Yeah. That can vary from utility to utility based on the generating equipment source. They tell, hey, what is the ramp rate they can tolerate? Based on that, we have to slowly go up. But the AI workload doesn't go up in a step fashion. They go instantaneously to the 100%. So that's the challenge we have to solve at the data center level.
Got it. So what are the type of challenges do we see in terms of AI workloads in the context of power management?
Sure. The one thing we talked about is the load swings. The next one is electrical design power, are sometimes called as EDP, or sometimes people call it as a spike power or a peak power. What that means is, let's say if you take a rack which has got several GPUs and a network switch in it, it can be, let's say, 100 kilowatt per rack. But if you zoom in and look at how the power varies at the millisecond level, it can even go to like 150 kilowatts. That's like 50% more power when compared to the normal 100 kilowatt. So if a one rack goes to 150 kilowatt in a big data center, it's not a problem at all. We can handle it. But right now, the AI workloads, several 100,000 GPUs are running the same job. Imagine if all of them go up by a 50%. So on a 1 gigawatt data center, all of them went to 1.5 gigawatt. So that's really a hard challenge. That's a new challenge that we have to address.
Well, so the whole EDP that you mentioned, it's actually very similar to the turbo mode in CPUs. That has been there forever. So it's conceptually speaking, it's not new. When the load comes up, there is a possibility that you can actually draw a lot more power and give a big performance boost until the chip heats up. And then once he heats up, you kind of need to level down so that the thermal profile of it and the cooling infrastructure can catch up to it. So essentially for a small period of time, you get a big boost in performance, and then it tapers off. But what I'm hearing is that, with the AI infrastructure, it's very similar, except it happens in a matter of milliseconds or 10 milliseconds, and most importantly, it happens in a concurrent fashion across 100,000 GPUs or more. And then it keeps happening every minute or even every second, if you will. So it's almost like continuously happening. So how do you actively manage this kind of load oscillations, both upstream to the grid as well as in the data center itself?
We deploy multiple controls and solutions at various layers. So at a high level, there are 3 levels you can control this. One is through software mechanism. Another one is through GPU and accelerators. They provide a functionality to dampen the power swing. Third one is you can use energy storage or capacitors to dampen. Let's look at one by one. The software-based mechanism, you can run a useful workload or a dummy workload so that the power doesn't drop, so that the power is almost constant.
So that's like, during a checkpointing, you run some other workload, if you will, to keep the GPUs busy. And maybe it's a dummy workload, maybe it's a useful workload, but nevertheless, inject some workload during the checkpointing of the entire cluster.
Yeah, exactly, you're right. So that's the one option. Or it all can be a combination also. The second one, we have a tool in our tool chest is the GPU and AI accelerator chip vendors. They provide a functionality that you can use to slowly ramp up. You can set a rate saying 1% or 0.5%. So it slowly ramps up the GPU power instead of instantaneously going up. The same thing you can use to coming down also. It can slowly bring the GPU power instead of straight away coming from 100% to 30%. That's in addition to that, the vendors provide additional functionality where you can set the minimum floor so that while the workload is running, it doesn't really come down like below 90 or 80%. So that's the second tool we have in our tool chest. The third one is the energy storage system. Within that, it can be at 3 levels. One is within the rack. Sometimes people call that as a supercapacitor shelf or a capacitor within the rack itself. So that can dampen, that can help in dampening sub-second oscillations. Since you cannot put a lot of capacitor shelf within the rack, you don't have a lot of room in it, so it can help you to dampen maybe few seconds of the power oscillations. That's one. The next one where you can put the energy storage is enhanced UPS, so where you can add additional storage. The third one is at the campus level, you can deploy energy storage system so that you can dampen the power swing so utility doesn't see it. So these are the 3 tools we have in our tool chest. We use them to dampen the AI load power swings.
Got it. So, essentially you have software, and then you have, a chip level, ramp rate, functionality. And with both those scenarios, essentially all the chip is doing is it's just burning off electricity, if you will, even though it's actually not doing any useful work, just to, keep the load, smooth. I think the one thing that occurs to me is that, with the, particularly with the chip level functionality where you essentially, use the GPUs themselves as a load bank in this case, it's just like a resistor, you just burn off electricity. It's not as energy efficient, so it's generally, you can use this, but then having energy store at data center level in some fashion or form is also better from energy efficiency standpoint.
Yes, exactly, you are right. So in the energy storage system, what we are doing is, in our example, when you are going from 30 to 100%, instead of going instantaneously, you go at 1%, but you are discharging from the energy storage so that the IT load can instantaneously go, but the utility doesn't see this. Same way, when there is a load dip, we start to charge that energy so that we are not wasting. So you charge it and then again use it when you want it. On the other hand, like you said, if you use a dummy workload or if you use the GPU, you are burning energy to maintain the constant power.
Got it. How is the the enhanced UPS and the battery energy, or general energy storage system differ from any of that?
Right. So the traditional UPS system already have battery. Hey, why can't that be used to dampen the power swing? Why do we need enhanced UPS? Right. So the standard UPS uses the lead acid batteries, and they are not rated for frequent rapid transit and high life cycle fast charge discharge rates. So they are mainly meant for, let's say if the utility power goes down, so if you want to bring up a generator during that time, that UPS battery you can use. So that doesn't happen often. But the AI workload, when you want to use those batteries, you are using it every hundreds of milliseconds. So you need a different type of a material that can support frequent rapid charge and discharge cycle. So that's the enhanced UPS that can support these AI workload requirements.
So essentially you have a different type of battery that can support frequent, charge and discharge cycle. And in addition to that, the UPS is generally, designed to protect, the IT gear, if you will, in the data center from the chaos that's happening in the grid, if you will. But with this use case, you're actually inverting it. You're actually, the chaos is inside the data center, and we are protecting the power source and the grid from the chaos that's happening within the data center. It's a very different use case, but the same sort of batteries and the inverters and the control logic, you can essentially enhance it to protect the grid and the power source from the chaos in the data center. If you step back and look at what's going on in the power industry in response to a variety of things, including rolling outages that we have seen across the world in recent times, there's been an increased pressure around having additional restrictions or specifications for large loads that are connected to power infrastructure. And how do we solve some of that?
Low voltage right through, or LVRT. Sometimes you might have heard about that when you hear about blackout news. What that exactly means is due to some issues in the transmission line, so the voltage can sag maybe by 50-60%. The nominal voltage is anywhere between 90 to 110%. When the UPS sees that now the voltage is like around 50 or 60%, it immediately switches to the battery. That's the whole purpose of the UPS. UPS is doing its job. So what is the problem? So now you have dropped off 1 gigawatt of load from the utility. Let us say there are like 5 other data centers in the region. They all will recognize that voltage drop and they all will drop that load. So there is a 5 gigawatt of load drop. So what happens on the utility side is there will be a frequency increase. Once it crosses a certain threshold, it will trip. There will be a blackout event. That's the one we are trying to avoid.
That makes sense. It's almost like a positive feedback loop within a grid, where something happens, and in response the load withdraws, but then that triggers a bigger reaction, which then causes even more loads to withdraw. And then in some cases the power generation themselves might withdraw. Like, hey, this is something is happening, so let me actually cut myself off. The breakers go off, and then now suddenly there's no power on the grid, and that essentially what causes chaotic rolling blackouts, where the power comes on and off as perceived by the end customer, right?
Yeah, exactly. So the requirement is once this happens, you switch to the battery, but utility asks you to consume as much as power from the utility, and for the remaining use the battery from the UPS. Once the problem is solved, let's say if it's solved in the next 100, 200 milliseconds, utility asks you to put the load back within 1 second on the grid so that the power generating equipments don't see this huge drop, so we can avoid the blackout events. So how we solve that problem is, in our enhanced UPS, we have the capability to support low voltage right through, so that if you see this problem within 1 second, we can put the load back on the utility grid. That's how we solve the problem.
It's not a brand new problem. What's different is that the things that the grid providers need to worry about are large loads that happen, do something in a synchronous fashion. And in the past, data centers are not that big, but now we have gigawatt campuses that are coming up, and that essentially means that we need to take this, this becomes an integral part of the power grid, if you will. So let's shift the focus to cooling. Now, we've had data centers for a long time, so there's nothing new about that. And we have air-cooled racks, but these AI accelerator and GPU racks are very, very dense in order to get the network latency really, really low. And that essentially creates unique, cooling problems. So can you talk about, how do we approach thermal management, particularly with the advent of ultra-dense GPU racks?
Air cooling simply cannot keep up past 30 kilowatt per rack due to air's low volumetric heat capacity. For example, today's GPU racks are already in the 100 kilowatt per rack. Vendors are coming up with 500 kilowatt per rack, 1 megawatt per rack. All of those needs to be liquid cooled. There are some portions still air cooled, but majority of the components within the rack are liquid cooled. So there are 2 loops for liquid cooling. One is called as a facility water loop. Another one is called as a TCS, or the technology cooling system loop. The technology cooling system loop is the one that touches the GPUs. So there is a cold plate on top of the GPUs. There are micro channels in the cold plate. So the liquid goes through the micro channels, and absorbs the heat and brings it back to the CDU or the coolant distribution unit. That's where the heat is transferred. And then there is a water-cooled chiller. It's also a closed loop. Then there is another dry cooler. That's the one for rejecting the heat. Our design goal is zero net water consumption. Both the TCS loop and the facility water loop or the external chilled water loop both are 100% closed loops. Additionally, heat captured is ultimately rejected via the dry coolers. So there is no evaporative coolers. There is no chiller water usage in our data centers.
Well, that's great. So essentially, what we do is have a, two fully closed, a cooling system. The one inside the data center is TCS, the technical cooling system, which has more of a purified water, with the antibacterial agent. And then that is the thing that's actually qualified or, suitable to go in the microchannels in the cold plate on top of the chip. And then the heat that's coming out of that is then exchanged to an outer chilled water, which is also a closed loop. And then that water then ejects the heat through outside chillers in the atmosphere. And obviously, the chillers we have closed loops so that we don't lose water. And the chillers also, do not use water. We do not use any evaporative mechanism. We just use dry coolers there in order to, do that chilling mechanism without any water consumption. Yeah?
Yeah, exactly. Yeah, that's why we use the dry coolers to reduce the water usage. Yeah.
Awesome. Cool. Well, thank you for joining me today, Ram.
Thank you, Pradeep.
Here are some of the key takeaways from our conversation on OCI data center innovations. The challenges of modern data center power loads are influenced by factors such as load size and synchronous workload fluctuations. Modern AI workloads demand dynamic power management that are addressed by a combination of capacitance, energy storage systems, GPU hardware-based ramp controls, and software-based ramp controls. Advanced voltage and load regulation capabilities are essential for large data center campuses going forward in order to be good citizens of the power grid. Direct-to-chip liquid cooling allows high-density AI infrastructure to be cooled properly. And OCI uses closed-loop cooling with dry coolers that use zero water in order to minimize the environmental impact and be community-friendly. Thank you for joining us today.